So everything you learned in units 9 or chapters 9 and 10 in chapter 11 is times 2. So we're going to look at comparing two means. We're going to look at comparing two populations, two proportions. So everything's times 2. It's actually, I feel like, more real world like, because oftentimes you are comparing two things. Like, I compare classes all the time. Now, we don't ever do 3. That's beyond this class. We just stick with 2. So, like, salaries of men versus women. Think about your sampling techniques. A new drug versus an old drug. Or a placebo versus a new drug. So, it's always comparing. Usually, if we're doing a hypothesis test for two proportions two means, this is usually your null hypothesis, that the mean 1 is going to be equal to mean 2. Okay, you're assuming like that the drug and the placebo work the same amount, or that first hour and second hour are going to have the same average, and then we compare either greater than, less than, or not equal to. Okay, so make sure that you realize two samples can be independent if the selection of the individuals that make up one sample or one treatment group does not influence the selection of those in the other sample or the other treatment group. So today we're going to look at independent samples. If they are matched in some way, you should tell me this was fuzzy, or they're not completely independent. This is paired, and we'll look at that when we get to 11.2. Paired can be like the same group of people, like a pre versus a post test, or if I match you based on some meaningful thing. But we'll get to paired in 11.2. Right now, for today and tomorrow, we're going to look at independent. Okay, so you're going to have two separate samples. So men versus women, first hour versus second hour, something like that. We can also, like, if we're assigning subjects to treatments in an experiment by drawing names out of a hat, or remember we did the random number generator and we would split them into two groups, those are considered independent. So if you have like 100 people and you say I'm going to split 50 into group 1, 50 into group 2, that's also considered independent. Okay. So when we get two populations, you're going to have two means. So we do mu1, mu2. Sometimes, like, you can use, if you don't want to use 1 and 2, you can use different letters, M and F for male, female, something like that. Your variance will be sigma 1 squared, sigma 2 squared. Standard deviation would be sigma 1, sigma 2. So that would be for the population. This would be if we were doing a Z test or Z interval. For your sample, you can have two different sample sizes. The sample sizes do not have to be the same. They just have to be greater than 30 each. Okay, one can be 31 and one can be 36. Like, first hour, you guys have 32 people. Second hour, there's only 28. Okay. The mean would be x bar 1, x bar 2. Variance, S1 squared, S2 squared. Standard deviation, S1, S2. Bless you. So when I ask you, remember how in like chapter 9 and 10 I said list all your information? You're not going to give me variance. You're going to give me 6 things this time. So before you only had to give me 3, now you're going to give me 6. Now, how does the mean of the difference look? Variance of the difference and standard deviation look? Basically, if I want to find the mean of the difference, I just subtract the two means. Mean 1 minus mean 2. The variance and the standard deviation look a little funky. Bless you. The variance is sigma 1 squared over n1 plus sigma 2 squared over n2. So this is your standard deviation. sigma 1 squared over n1, sigma 2 squared over n2. This is on your formula sheet. So when we go to do our write-ups, you remember I always make you write the formula. The formulas get a little bit more complicated. But again, they're on the formula sheet. This is your new, we've been using these two in chapter 9 and 10. This is year 1 for chapter 11 right now. We'll get to this later. And this later. Okay. So, how do you do a write-up when you're comparing two means? So today we're going to look at, here's all 8 you're going to learn in chapter 11. We're focusing on 2 sample Z test, 2 sample T test for today. Eventually you'll see all of these. So our first condition is the same, except there's one, usually it's always that it's a random sample, but now you want a random sample and independently selected. It won't always say like they were independently selected. If you have 2 separate groups, like I said, men, women, or if it looked like they broke up one group into 2 groups for whatever reason using a random number generator, you can assume they're independent. Now, you got to check for condition 2 that N1 and N2 are both large. So N1's got to be greater than 30, N2's got to be greater than 30. So then you can say both sampling distributions are approximately normal by the central limit theorem. Or you can have the population distributions are already normal. Or you can construct 2 box plots, which is the worst one. And you basically do 2 box plots on one graph. And then if your population standard deviation is known, we're going to do a 2 sample Z test for comparing means. And then, so this is condition 3. Condition 4, you have to tell me what mu1 is and what mu2 is. And this is very important because depending on what your ho and ha are, you can flip your mu's around. I need to know which one's which. Like first hour versus second, men versus women. Your Z value, here's your formula. This is going to be the division sign. So it's x bar 1 minus x bar 2 minus, that should be a minus, not a plus, minus some hypothesized value which the majority of the time will just be 0 because you're just assuming that they're the same, divided by the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. Everything else is the same. The ho and the ha, there's 2 ways to write it. I'll show you both, and then I'll tell you which one most people end up doing. Usually our null hypothesis is mu1 minus mu2 is equal to some hypothesized value. This would only work if the question was like, I want males to make $1 more than females. That's what I'm trying to prove. Then that's your hypothesized value. What we normally end up doing is down here, where mu1 equals mu2. I'm just trying to figure out, do men and women make the same amount of money? So this would just depend on the question. But the majority of the time, you're going to be doing this one. Mu1 equals mu2. And then our alternates are the same 3. Greater than, less than, not equal to. So you either have mu1 minus mu2 is greater than your hypothesized value mu1 minus mu2 is less than your hypothesized value, or mu1 minus mu2 is not equal to your hypothesized value. Or, don't worry about that, mu1 is greater than mu2, mu1 is less than mu2, or mu1 is not equal to mu2. So this is why, if you do it this way, I got to know which one's 1 and which one's 2. That's why condition 4 is so important. Because otherwise these two could be flipped around. Okay. In your calculator, everybody get your calculators out. This test is test 3. So 2 sample Z test. That's number 3 on the calculator. Now, this all works if you know both population standard deviations. What you're going to do more often, like we did in chapter 9 and 10, is use a t-test. But it's the same thing. Simple random sample and independent. I can't spell. Independent. Don't mind that. N1 and N2 are both greater than 30. So if we don't know this, it's a 2 sample t-test for comparing means. And again, condition 4 is tell me which one's mean 1 and mean 2. Can I flip it? Your t critical value is, again, x1, x bar 1 minus x bar 2 minus some hypothesized value if I give you one. Like I said, most of the time it's just 0. Divided by, now this would be s1 squared over n1, s2 squared over n2. Now, normally, with a t distribution, you got to have degrees of freedom. And what are usually our degrees of freedom? Just n minus 1. But now you have 2 different n's. They can be different sizes. So, there's a formula for degrees of freedom. You do not need to know this formula. The calculator will give you degrees of freedom. Because just write down what I write down, but you don't need to know it. Because we're going to do a v. v1 plus v2 squared divided by v1 squared over n minus 1, v2 squared over n minus 2. 1. That's n1 minus 1, n2 minus 1. Where v1 is the standard deviation squared over, Basically, just write yourself a note. Find on calculator. It's not as simple as just taking the sample size minus 1. I will never ask you this. I have never seen it on an AP test being asked. Most of the time, they just want you to use your calculator. So, which one do you use? You want to use number 4. 2 sample t-test. Now, when you do a 2 sample t-test, when you get down to the bottom, it's going to say, do you want it pooled? Yes or no? Just say no. You don't even know what it means. Just say no. Also, it's going to give you degrees of freedom of a decimal. Remember, you always round down. Okay, that way our estimate is more conservative. Because it'll say like the degrees of freedom is like 15.7. Just round down 15. Okay, let's do an example so we can put this all together. Your conclusions are going to be the same-ish. So we'd like to compare the mean fill of a 32-ounce cans of beer from two adjacent filling machines. Past experience has shown that the population standard deviations of the fills of the two machines are known to be 0.043 and 0.052. A random sample of 35 cans from machine 1 gave a mean of 16.031, and a sample of 31 cans from machine 2 gave 16.009. State, perform, and interpret an appropriate hypothesis test using a 0.05 level of significance. Okay, so let's start with our conditions. Do we have both random samples and they're independent? Machine 2 didn't have a random sample, but machine 1 did. They're independent because they're two different machines. So that's that independence there. So we can say both samples are independently selected. However, only machine 1 was a random sample. Proceed with caution. Now, when you go to have your test and quizzes and stuff, this can the two conditions should really be met. Okay. Now, look, are both greater than 30? Yeah, 35 is greater than 30. 31 is greater than 30. Therefore, both sampling distributions are approximately normal by the central limit theorem. So all we're adding is both in condition 2. So are we doing a z-test or a t-test? Did you have the population standard deviation or not? Population standard deviation, population standard deviation. So this is a 2-sample z-test for comparing means. Now, you gotta, like I said, the most important one is that you tell me which one's mu1, which one's mu2. Now, there's two machines, 1 and 2, so we're just going to stick with 1 and 2. So this is going to be the true mean fill of machine 1, true mean fill of machine 2. Now, I don't care if on your homework, you know how you can use the quotes and it means like you bring down whatever. I don't care if you do that on homework, but when you're doing a quiz or test or on the AP test, make sure you just write it all out. Remember, you're only going to have like at least one of these on the AP test. Okay. So for our testing section, there's no hypothesized value here. We're just looking at, are they the same or not? So for our null hypothesis, we're going to say mu1 is equal to mu2. Our alternate is that mu1's not equal to mu2. So this is still the same. It's a 2 two-tailed test is you're going to end up with one z-value, positive, negative. So this part doesn't change from chapter 10. Okay, it's still a two-tailed test. We're just looking at, are they the same or are they different? So when you do your test statistic, it is nice to, the reason I like to get you started on writing out all your stuff is because it's nice to, it's just easier to organize to put into your formula or to put in your calculator. So I don't care what order you give it to me. So N1 was 35, N2 was 31, sigma 1 was 0.043, sigma 2 was 0.052, X bar 1 was 16.031, X bar 2 was 16.009. Do we have an alpha? Yes. 0.05. Now, if this was a t-test, you would want to put degrees of freedom, but just leave it blank until you do everything in the calculator. Okay. So your z-score, subtract your 2, so it's 16.031 minus 16.009. Really minus 0, but honestly, I don't really care if you write that. Over the square root, 0.043 squared over 35, 0.052 squared over 31. So far, so good. Okay. Now, go to your calculator. We're doing a 2-sample z-test. So then just plug in. That's why I like it organized here, because then it's organized to put in. Because you're going to flip back and forth between 1 and 2. Bless you. And then you can either hit calculate or draw, like we've been doing. I'll hit draw. So you got your two-tailed test. Here's your z-score. Here's your p-value. So 1.859. So we have negative 1.859 and positive 1.859. A lot of you wrote both of them on your test, which was totally fine. So a z-value of 1.859 gives us a p-value of 0.063. If you're doing a t-test, the only thing is you don't want to hit draw, because then you can't figure out your degrees of freedom. So if you do a t-test, you want to hit calculate. Now the conclusion is the same. So is this greater than our alpha or less than our alpha of 0.05? Greater. So we're going to fail to reject. So since our p-value is greater than our alpha of 0.05, we have evidence to fail to reject the claim that the true mean fill of machine 1 is the same as machine 2. So with your it appears, the second sentence you should say, if you're sticking with the hoe, It should be like they are the same. If you're going with the alternate, you could say they're different. One's greater than and one's less than. So it appears the machines fill the cans with the same amount of beer. Or answer the question. Okay. So, questions on this. Like I said, we probably should put something about the proceed with caution. Sorry. However, sample 2 was not random. Concerned about the validity of the test. But honestly, you should not have to write that on a quiz or a test. We try to make sure that all the conditions are met. Okay, questions on the 2 sample stuff? Yes, Alex.
What would the hypothesized value look like?
If I gave you, like, we're trying to figure out if machine 1 gives 1 more ounce or 2 more ounces, then it would be like mean 1 minus mean 2 is equal to 1.
I got you.
If the difference was some other number besides 0, if you're not looking for the same. But that has to be given to you in the problem.